Approximate integration. Consider the definite integral, the integral from a to b of f of x dx. Sometimes it's impossible to evaluate a definite integral. Maybe the function in the integrand has no known antiderivative. Maybe the function itself is derived from data. But we can still use Riemann sums to approximate the value of the definite integral. We begin by partitioning this interval, a to b, into n subintervals of equal length delta x. Well, delta x is b minus a over n. We choose a notation, let x sub I be equal to a, which is the left side of the integral, plus I delta x, where I is equal to 0, 1, 2, 3 out to n. Now, depending on the choice of x sub I, there are three different approximation techniques. There's a left sum, a right sum, and a midpoint rule. If x sub I is any point on the interval xi time 2 over to xi plus 1, then the definite integral from a to b of f of x dx may be approximated with the Riemann sum, I equals 1 to n of x of f evaluated at x sub I star dx. Now this general Riemann sum will be used for our left sum, right sum in our midpoint rule. We'll see two more rules, the trapezoidal rule and Simpson's rule. That will give us 5 different approximation techniques that we'll cover in this lesson. For the left sum, x star I are the left endpoints of each rectangle. So you see before you a curve y equals f of x. We would like to approximate the area between the x-axis and the curve. The way we do this is we sum up the areas of these rectangles. The height of each rectangle is given by the distance of the left side of the subinterval from the x-axis up to the curve. So we can approximate the definite integral by delta x is equal to, by delta x times the quantity f evaluated at the left endpoint x sub 0 plus f evaluated at x1, and we continue all the way until we get to f of x sub n minus 1, the left side of the last rectangle. Recall delta x is b minus a over n. The right sum is calculated by allowing x star sub I to be the right endpoint. And so the right side of the rectangle will be what will be the height. It will be the right side of each subinterval. Again, we have the same notion of an area under a curve, but notice in this picture, unlike the previous one, the heights of the rectangles are given by the right side of the rectangle touching the curve. And the definite integral is approximated by delta x times f of x1 plus f of x2 plus, and we continue until we get to f of xn, or f of xb. Again, delta x is b minus a over n. For the midpoint rule, x star sub I, the notation is used x star, because these will be the midpoints of each subinterval. They will have to be calculated. When you take a look at the picture, notice for each rectangle, the middle of each subinterval, the distance from the x-axis up to the curve represents the height of the rectangle pertaining to that subinterval, and the definite integral is approximated by delta x times f of x1 bar, and that is the midpoint in the first subinterval, plus f of x2 bar, which is the midpoint for the second subinterval. And we continue until we get to the midpoint of the last subinterval, and we evaluate f at that x value, f of xn bar. Each x bar I is found to be the midpoint for each subinterval, so we would take 1/2 xi plus 1 and determine each particular midpoint. And again, delta x is b minus a over n. The trapezoidal rule is found by summing up trapezoids. So when you take a look at a picture, what you notice is not a series of rectangles that are approximating the area of the curve, but a series of trapezoids. Recall the area of a trapezoid is 1/2 height times the sum of the base 1 and base 2. If you look at the very first trapezoid, the base 1 is given by the left side of this trapezoid and base 2 the right side. So 1/2, the height would be 1/2 delta x, which I'll highlight, times base 1, f of x 0, plus base 2, f of x 1. When you look at the second trapezoid, notice 1/2, the height is 1/2 delta x, times f of x 1 plus f of x 2. So, with the exception of the first and last height, each of the subsequent heights are counted twice in this calculation, where each height from the x-axis up to the curve will be respectively the right side of the previous trapezoid and the left side of the subsequent trapezoid. The formula itself is delta x over 2 times f of x 0 plus twice f of x 1 plus twice f of x 2, and the pattern continues until you get to twice f of n minus 1, and then finally plus f of xn. So let us use the left sum, right sum, and midpoint rule and trapezoid rule to approximate, where n is 4, the definite integral from 1 to 4 of the square root of x dx. First, let's find the value of delta x. Well, that's b minus a over n. 4 minus 1 over 4 is 3/4, 0.75. We will use this delta x as 0.75 in each of these 4 calculations. X sub 0 is 1. If I add 0.75 to 1, I get the value of x1, 1.75. Add another 0.75, I get 2.5. Add another 0.75, I get 3.25. And finally, I get to the right side of the interval. 3.25 plus 0.75 is 4. For the left sum, if I look at my picture, I've partitioned the interval from 1 to 4 into 4 different subintervals. I've labeled the endpoints, 1 and 4, and then the endpoints of each subinterval. For the left sum, we would take delta x times f of x 0 plus f of x 1 plus f of x 2 plus f of x 3. Well, that means we're going to be evaluating the function at 1, 1.75, 2, and 3.25. And when we do, we get approximately 4.280092. For the right sum, we have the same picture in front of us, with the difference being that the right side of the rectangles are now touching the curve. We allow ourselves to approximate by having delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. So now we're evaluating at 1.75, 2.5, 3.25, and 4. And when we do, we find the result to be 5.030092. For the midpoint rule, we first have to find the midpoints of each interval before we can begin. So, once we do that, we then draw the rectangle so that the midpoint of each interval, when we evaluate the function there, that represents the height for each subsequent rectangle. How are those values of 1.375, 2.125, 2.875, and 3.625 determined? Well, you just simply take 1/2 times 1 plus 1.75, 1/2 times 1.75 plus 2.5, and you continue. The second way to evaluate these midpoints is to find the very first midpoint, 1.375, and then add delta x to it. 1.375 plus 0.75 is 2.125. Add another delta x to that. 2.125 plus 0.75 is 2.875. Add another delta x to that. 2.875 plus 0.75 is 3.625. Once we have the midpoints, we can then evaluate using the midpoint rule by taking delta x, 0.75, and evaluate the function at the 4 midpoints. The result is 4.672400. Lastly, we look at the trapezoidal rule. Delta x over 2 times f of x1, and then we take twice f of x2, plus twice f of x3, plus twice f of x4, and lastly plus f of x5. Again, each subsequent height is represented by the left side and the right side of a trapezoid. It's counted twice, with the exception being the first and last heights. So we look at the picture, see the area under the curve approximated by trapezoids, and we substitute in. Delta x is 0.75, delta x over 2 is 0.75 over 2, times the function evaluated at 1 plus twice the function evaluated at 1.75 plus twice the function evaluated at 2.5 plus twice the function evaluated at 3.25 plus the function evaluated at 4. The result, 4.6550926. The integral itself can be actually evaluated directly in this case. You can take an antiderivative and apply the fundamental theorem of calculus and find that the antiderivative evaluated with an upper limit of 4 and a lower limit of 1 and then subtracting the results gives you 14 over 3 or 4 2/3 or 4.6 repeating. And so that means when you take a look at the errors that the four methods would yield, when n is 4, the left-hand approximation is off by 0.386. The right-hand approximation is off by roughly negative 0.363. Midpoint approximation is off by negative 0.006 roughly, and the trapezoidal approximation is off by roughly 0.012. Few remarks that we can make. The trapezoidal rule and the midpoint rule are more accurate in general than the left and right-hand sums, in that the error in the midpoint rule is approximately half the error of the trapezoidal rule. We have a fifth means to approximate a definite integral, and that is with Simpson's rule. Here, each consecutive pair of intervals on the curve y equals f of x is approximated not by a rectangle, not by a trapezoid, but by a parabola. Picture you see in front of you indicates that if you're trying to find the area under the curve y equals f of x from x sub 0 to x sub 8, you would like to approximate, you would find the area underneath each subsequent parabola. To use this particular method, n must be even, and the actual formula is given by delta x over 3 times f of x0 times plus 4 times f of x1 plus twice f of x2, and then the pattern continues. 4 times f of x3, twice f of x4, plus dot dot dot, and eventually you come to the endpoint, the 4 f of x and x minus 1 plus f of xn. The pattern is 1, 4, 2, 4, 2, 4, 2, and you continue until you come back to 4 and then 1. If I want to approximate using Simpson's rule, that same definite integral, square root of x dx on 1 to 4, again recall, we had a picture in our mind. We had a delta x of 0.75. Subintervals were marked by 1, 1.75, 2.5, 3.25, and 4. Delta x, b minus a over n of 0.75 is now plugged into our new formula, delta x over 3 plus. And then we are very careful to write the quantity f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, and we finally get to the endpoint f of x4. Substituting in delta x is 0.75, and substituting in 1, 1.75, 2.5, 3.25, and 4, we find that our approximate area under the curve is 4.666220708. The error is much smaller than the other methods, if you notice. It's 4.46 times 10 to the negative fourth. Well, clearly, as we increase n, we would expect that the area under the rectangles or trapezoids or parabolas to be closer to the true area under the curve. And therefore, we would expect as you increase n that the error between the exact area and your approximated area would decrease. As n increases, the error would decrease. But let us compare the errors. Notice the table that is before you and make some remarks about what we see on this table. First, when n is multiplied by 10, so you take 4 as the number of rectangles, trapezoids, or parabolas, and you multiply it by 10 to get 40 rectangles, trapezoids, or parabolas, or multiply by 10 again to now get 400 rectangles, trapezoids, or parabolas. There are patterns that emerge. The errors in both the left and right sums decrease by a factor of 10. When n is multiplied by 10, the error in the trapezoidal rule and the midpoint rule decrease by a factor of about 100. And the errors in Simpson's rule decrease by a factor of about 10,000. So we can extrapolate and say, listen, in general, when n is multiplied by k instead of 10, but by k, the error for the left and right-hand sums decrease by a factor of about k, while the error for the trapezoid and midpoint rules decrease by a factor of k squared. And the best of the approximations, Simpson's rule, here the error decreases by a factor of about k to the fourth. Thank you.